So we have something of a conundrum here. We have the straightest possible world line has a curvature, right? Remember this curvature, the second derivative, gm over r squared. How can it be that the geodesic, and all the properties of a geodesic, given the beginning, the initial tangent, you can reconstruct uniquely the whole extent of it, right? It's as straight as possibly be at every point. It has all the properties of a geodesic. Just it's curved. All right, so the problem is that we're going about it in a mixed, naive way. We're saying we have the space plus time. We don't know what the geometry of this space plus time is. We're going to try to find it. We try to define it according to straightness, according to inertia. We found there's no such thing as inertia. So we have a more sophisticated space plus time. So we can't draw axes like an x and t axis in our flat, ordinary, unsophisticated piece of paper and expect that the diagram that we're going to get is actually representative of what's really happening in space plus time. We would need to be in free fall frame on some kind of a whatever and draw thing. Now, when you draw a gravitational world line, you just draw it as a curved, right? It's accelerated, so it's a curved line. But you're drawing that again in this non-sophisticated space plus time connected area. You would have to kind of twist the axes in some way to represent this sophistication of the space plus time, and then draw this line. If you did that, you would find that the free fall world line was in fact the straightest possible line. Okay. At this point, we're ready to jump into general relativity. Up to this point, we were kind of neo-Newtonian. I didn't really introduce anything that's not Newtonian. No special relativity. You know, there wasn't anything that Newton, in theory, couldn't have followed immediately. He even knew about free fall. He computed some very nice riddles, and he used these properties of the equivalence principle in computing things. There's nothing really non-Newtonian, but it's kind of neo-Newtonian, especially talking about space plus time and the idea of these parallel lines and defining these straight lines, defining straightness, and so on. Now, to jump into general relativity, what we would say is, okay, we have this interesting property where the straightest possible lines seem to be curved. We understand that we took too naive a view of what space plus time is. So let's say that space plus time is warped relative to our usual conception, and the straightest possible lines, when represented in this wrong frame, turn out to be curved. But if you would draw them correctly, they would be straight. In other words, space plus time is curved. The free fall world line is straight. If you want, you can think of our graph with space plus time and the curved world line for gravitational free fall. And by warping the axes in the right way, you're straightening out this line. So you get a straight line in a warped spacetime. If you look at that diagram the wrong way, like this, you get a curved line. Okay? And that's basically Einstein's theory.